Hey, ladies and gentlemen. Right, we're going to look at a new technique for taking integrals. This is kind of in our unit of special integration techniques. So we've just finished up working with our integration by parts. Now we're going to look at a technique called trig substitution. Now here's my example. We're going to take the integral of the square root of x squared minus 1 over x dx. Now, one thing that I want to remind you guys as the number of techniques here start to build up a little bit is don't forget where we've been before. And when you look at an integral, we should never jump to the more complicated possible technique when a simpler one could work. So if we go back to before our last test, we worked a lot on just a simple substitution. And when you look at this, and if I would have given you this problem before that last test or on that test, here's what I'm guessing you would have done. You would have said, let's let u equal x squared minus 1. And it's worth exploring. Okay? We want to do the simpler technique if possible. So let's just try just a normal substitution here. Let's let u equal x squared minus 1 and let's see what happens. All right, so we know that we need to find du dx. That's 2x. We have to solve for dx to substitute in there. And we have du over 2x. Now what happens when we do this substitution? We have the integral of the square root of u over x times du over 2x. So we've seen when substitution works really, really well when something cancels out, like this x down here in the denominator would cancel out with an x in the numerator. And that doesn't happen on this one. However, again, if I would have given you this on your last test or prior to the test, I think you would have continued to try some things. You would have continued to work through this just to see what happens. All right, I'm going to bring that 1/2 out front. And I'm going to have the square root of u over x squared du. And I have a hunch that you would have looked at this x squared and went, I don't want an x squared there, I want a u. So, do we know what x squared equals? Well, we know u equals x squared minus 1. So x squared equals u plus 1. So then we could do that substitution and change this to be the square root of u over u plus 1 du. And then we would have gotten frustrated here maybe a little bit, or maybe we wouldn't get frustrated, but we would have maybe come to the realization that we're stuck. If we had a binomial in the numerator and a monomial in the denominator, we would have been fine because we could just split that up into the two fractions. However, when we have a binomial in the denominator with this monomial up in the numerator, we can't do anything with that. So it was worth this exploration to see what happens, and we can see that just a normal substitution doesn't work here. So we need a new technique, and this is going to be called trig for trigonometric substitution. And you might say, okay, why trig? What substitution could we use with trig? And on our next slide here, I have a couple reminders for you of some identities. Okay, these are our Pythagorean identities from trigonometry, and these are the two that we'll be using most frequently as we do integration. So the first one is cosine squared plus sine squared equals 1. Okay. We know that. That's one that should be like ingrained in our brain, written on our heart maybe, okay, because we love that identity so much and it's so useful. So how do we see that play out here? Well, remember that there are more forms than just the way that it's written. Okay. I could instead write that cosine squared of x equals 1 minus sine squared of x. Or we could write it as sine squared of x equals 1 minus cosine squared of x. Okay, so we have multiple, three different ways to write that identity. How about tangent squared plus 1 equals secant squared? Well, another way to write that would be to say that, let's see here, tangent squared let's see here, I already got goofed up here. Tangent, no I didn't. Tangent squared equals secant squared minus 1. Now, look at this problem right here. And here we see something squared minus 1. And that sounds kind of like this. Secant squared of x minus 1. If the inside, wrong direction, if the inside here, x squared minus 1 was secant squared minus 1, we would have a square root of secant squared minus 1. And what is secant squared minus 1 equal to? Tangent squared. And can we take the square root of tangent squared? Yes, we can. That's just tangent. Okay? And that's kind of how this is going to run with our trig substitutions here. Can we use a Pythagorean identity to substitute in to have this work out pretty well through that process of substitution? Oftentimes there'll be square roots, not every time. It's okay. It's just we're going to see different things pop up. So let's go back to this first problem and let's try that substitution that I was just looking at. All right, let me grab this. Go to a new page. Okay. So, what's our substitution? We said it would be really nice if it was the square root of secant squared minus 1. We have x squared minus 1. So our substitution here is to let x equal the secant of, well, we need to change variables here, so we're going to be careful about this. Let's let x equal the secant of theta. Let's just call our angle theta. Let's not use x because x already means something. All right, so we're going to let x equal the secant of theta. Now, you notice that we are changing the variable, so we do need to find out what dx is. So let's take the derivative of this, which would be dx d theta. And what is the derivative of the secant of theta? Okay, so you have your derivative rule book, you have your integer rule book. Hey, take a peek in there. What is the derivative of the secant? And the derivative of the secant is the secant times the tangent. Okay, kind of interesting there. Let's see how this plays out. Remember, we're solving this for dx. So dx equals the secant of theta, tangent of theta, d theta. You know what, I should have given myself a little bit more room. Let's see if we can't. It's going to let me pull that over there. There we go. Let's slide it out of the way a little bit more. Okay, so let's do our substitution and let's see what happens. We have the integral of the square root. X is now secant, so x squared is secant squared of theta minus 1 over x, secant of theta, times dx. What does dx equal? The secant of theta, tangent of theta, d theta. All right, let's go for this. First thing I notice, secants of thetas cancel. Now we're going to work with that square root like we did on this page right there. Secant squared minus 1 is tangent squared. I guess I don't need to put that in the numerator because there's no fraction anymore. Square root of the tangent squared of theta times the tangent of theta d theta. This is, well, the square root of the tangent squared is the tangent, so we have the tangent of theta times the tangent of theta d theta, which gets us to the integral of the tangent squared. All right, so we got a much simpler integral here, don't we? And that's the goal of our trig substitution, is to get to a simpler integral. Now, what is the antiderivative of the tangent squared? Okay, what is that integral? Now, if we think back to our last section with integration by parts, I know that we did sine squared, we did cosine squared, we did some reduction formulas. Do you recall if we did tangent? Well, whether we did or we didn't, I don't think I even need to use integration by parts to do this one. I'm just going to use that same identity that we used earlier. What is tangent squared equal to? Secant squared minus 1. Now, why would I use that identity again? Well, who has a derivative of secant squared? Secant squared is the derivative of just the tangent. Minus the derivative, who has a derivative of 1? Well, theta has a derivative of 1. So we end up with this, the tangent of theta minus theta plus c. And that was a pretty easy integral to take once we had done our trig substitution. Now, let's not forget that we aren't done with this one yet. We have thetas. The original problem had x's. We need to substitute back in. All right, so what do we know about theta? Well, we know x equals the secant of theta. So what does theta equal? The arc secant of x. And we have to use the inverse secant to solve that for theta. So this is going to end up looking a little bit uglier for a moment, but then we'll figure out how to handle it. So this is the tangent of the arc secant of x minus the arc secant of x plus c. Now, I'm fine with this here. I really don't like the way that looks. Okay, how do we evaluate the tangent of the arc secant of x? Well, we have to go back to remembering how we did some stuff back in trig. And set up a right triangle here. All right, the arc secant of x, what does that mean again? It's the angle whose secant is x. Go back to this. X equals the secant of theta. So the secant of theta equals x. If this is my theta, the secant of theta has to equal x. Now we know secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. So for the secant of theta to equal x, we could have the hypotenuse be x and the adjacent be 1. Do you agree that the secant of theta now is x? X over 1, x. All right, now what do we want to find? We want to find the tangent of the angle whose arc secant is x. How do we find the tangent of this angle? Tangent is opposite over adjacent. So we need to know how long the opposite is. Using Pythagorean theorem, it's the square root of x squared minus 1. So what is the tangent of the arc secant? The tangent of the arc secant is the square root of x squared minus 1. And we have this minus arc secant of x plus c. So there's a first example for you guys with trig substitution. Using our Pythagorean identities, particularly when we see things that are squared and ones, we can use those identities. Now this is just one example. We're going to do a bunch of examples together. You're going to have to wait to the next video here to look at our next example. But good job. Thanks for sticking with me on that one. Let's go to the next video.